Hello everyone, I welcome you all to this channel Catalytic Guru once again. The previous videos we have been focusing more on topics related to chemical reaction engineering and catalysis. This time I've decided to take a break from all those and divert myself towards a new topic, thermodynamics. So I've written it as a friendly visit to thermodynamics, which means the first law of thermodynamics, which means it's a very informal way of explaining this. What I want you to do is see this video, then go back, pick up the statement of the first law of thermodynamics, read it, and I hope that you would understand. I'm not going to give the statement of the law in this video. I want you to go and read that after seeing this video. So before going into the first law of thermodynamics, I want to tell you a few things. So what you see above here is a closed system, and what you see below is an open system. So a closed system is something in which mass cannot enter or exit, whereas an open system is something in which mass can enter and exit. So if I ask you how will you supply energy to these systems, if you want to add energy or if you want to remove energy, as you can see, it can be done in three different ways. One is you can supply heat or remove heat by keeping a hot source or a cold source near the system, or if you can supply work or remove work. That can be done by piston or any other devices. And the last thing is, so these two things which I spoke about, you can do both for open and closed systems. But the last thing which you see, mass carries some energy. So when there is a mass, if you try to put mass inside a system, or if you try to remove mass inside a system, the mass added or removed will always have some energy associated with it. And in that way, energy can be added to a system only for an open system, because in a closed system, you cannot add or remove mass from the system. The mass of the component will be a constant in case of a closed system. It can change only in case of an open system. Right? Now, proceeding further, if I want to only focus on closed system initially, as I told, I will not give you the statement of the first law, but I will give you the mathematical statement which kind of tells you what first law is. So it says this. So the symbol you see before Q and before W states that Q and W are imperfect differentials, whereas U is a perfect differential, which means it can be integrated to give U2 minus U1 between two states. Graphically, I will try to explain you what this means. So if you have a pressure volume diagram like this, and I am defining you two states, I call this as 1 and I call this as 2. The state 1 is very well defined, which means the pressure is P1, volume is V1. We'll stop with this, and similarly it will have P2 and V2. Say if we need to go from 1 to 2, I might take this path, I might take a different path like this, I might take a totally different path like this. You can take infinite number of paths between two states, right? Path 1 and path 2. In any state, if I ask you what is the change in pressure, you will always say it's P2 minus P2. The path you take is not going to influence the value of dP or even dV or dt for that matter. It's always going to be V2 minus V1, or it's going to be T2 minus T1. But if I ask you what is the work that you supplied or removed to reach from 1 to 2 when you are going through, say I'll use a different, going through this purple path, it's going to be different from the other paths. Similarly, what is the amount of heat you supplied or removed? It's going to be different in every different case. So Q and W depends on the path you take to take from 1 to 2, whereas the other things doesn't depend on. So Q and W are the path functions, and other variables are state functions. There are other path functions too, which I don't want to get into details right now. For understanding the first law, you should understand that Q and W, the heat supplied and work done by the system, are path functions. And the other pressure, temperature, volume, all these things, internal energy, all those things are state functions. Right. Now, what does it have to do with the first law? As you can see from the expression, the left hand side of this expression is a difference between two path functions, whereas the right hand side is a state function. To make it more, to dilute the explanation, I would say, let's say you take 100 different paths between two given initial and final points. You take 100 different paths. 100 different paths will have 100 different values for Q and 100 different values for W. But you will be amazed to see the value of Q minus W in every case will be equal to a constant, which is du or u. Why it happens? Because that is basically what the first law of thermodynamics tries to say you, that the energy is conserved. The net value will always be a constant. Energy will always be conserved despite the path you take. Right? If you want to go from 1 to 2, energy will be conserved in that case. The effort you give is different, but when you finally add them all together, you will see the accounts being settled. That's what the first law of thermodynamics says you. I hope it was very clear to see the statement that left hand side is a difference between two path functions, whereas right hand side is a state function, which means the difference between path functions doesn't depend on the path. It's something like that, right? Okay. I will just motivated to give you one special case of this. There are 4 different cases where you will be studying in your undergraduate in isothermal, isobaric, isochoric process, adiabatic. I am just motivated to give you example only of an isothermal process. Why this is my favorite is what you will see though. I'm again going with the piston cylinder arrangement. Since I told you this, the process is isothermal. The change in temperature is associated with change in internal energy. So when I say isothermal, I have to go with du as 0. There is no change in internal energy. So what happens to the first law? It becomes Q is equal to W. Now I will assume some gas is present inside this and I am supplying heat. When I supply heat, what do you expect? The temperature increases and the gas expands. The gas expands and the piston moves up. When the piston moves up, again the pressure falls and the temperature falls, which means the temperature is not changing. So this is so beautifully done, where whatever the heat you supply is completely converted into work. It's a very slow process where you can see there is no temperature. You will be motivated to think that when you supply heat, the temperature will increase, but the temperature is not increasing in this case. Instead, whatever the work is being, the heat is being supplied is completely converting into work, and this cannot happen in a very real case, to be brutally honest, because that's what we will be seeing in the second law and all those things. But for now, I want you to just stay in the fantasy world and see how beautifully this happens. You supply some heat and it's getting converted into work. Imagine having such an engine for your bike. You supply some heat through the fuel and it's completely converting into work. You save a lot of fuel on those things. Okay, anyways, getting back, I just want you to give a glimpse of this open system. It's very similar to a closed system. Just to remember you this thing, when you write a law for the open system, this last things gets added up, because mass goes in and mass gets out. There is some energy associated with the mass and we have to account for it. Only that we have to include, everything else is the same. So I'll consider a system like this. It's like a piston cylinder, but it has an inlet and outlet. So this is something getting in. This is, I'll call it as m dot in, and I will call this as m dot out. I'll say initially M1 was present. There was some initial mass, and I'll say M2 is the mass of accumulation, or I'll say just accumulation. When you write the balance, this is my control volume, so I'm writing the balance over this zone. So what happens here is the same Q minus W will be there. Q minus W will be there. It will be equal to, you see, mass is getting in, so M out will be there. It's in minus out, right? Sorry. It's M in and U in minus M out, U out. Okay, so mass getting in with its energy minus mass getting out with the corresponding energy, plus M2 U2, right, minus M1 U1. So this is what we have, along with, since the mass is entering and exiting the system, right? The mass is actually entering and exiting the system. We have to account for it. So I will call it as M in. Whatever is coming in, it will have a flow energy. Due to flow, there will be some energy. Similarly, minus M out will have some energy associated. Right? So this is what we have. Now, this you can see mathematically, you can add these two terms, this and this, right? So I am adding this U in and this PV in, and I am naming it as H in. And similarly, this will be M out and H out, but the rest things will be the same, M2 U2 minus M1 U1, where H is equal to U plus PV, where H is called the enthalpy. So enthalpy is nothing but it's like internal energy. It's associated with temperature, but it carries the flow energy along with it, the flow work along. Since the material is flowing, there will be some pressure volume changes associated with it. So enthalpy includes that as well. As you can see, this M2 and M1 are not crossing the boundaries, so it will just have the internal energy. It will not have the flow energy. Whereas M in and M out are flowing, so it will have the flow energy along with the internal energy. We call it as enthalpy. I hope the first law of thermodynamics was clear for a closed system and for an open system. The limitations of the first law and how it can be overcome, and the other few things can be soon seen in another video. Till then, please like, share, subscribe my channel and this video. If you have any feedbacks or suggestions for more videos, please let me know through the comment section or the email catalyticguru@gmail.com. Thank you so much for listening.